shall we begin? What time is it? Yeah. Okay, welcome everyone to the Simons Institute. My name is Sampath Kannan. I'm the Associate Director. Welcome everybody. No? It's not working. Let me try this one. Welcome. Is that better? Welcome everybody to the Simons Institute. No, it doesn't sound like it. No? Hello, testing. Yeah, that's better, right? No, me? No? Okay. Anyway, this is not too important, so it doesn't matter if it gets recorded or not. So welcome everyone. For those of you for whom it's the first time here, I'm not sure there are any, just a word about the Simons Institute. It was funded by a generous grant from the Simons Foundation in 2012. And it's a venue for bringing together top theoretical computer scientists in focused areas for sustained collaborations, and it's the only one of its kind in all of computer science. But not only do we have programs in theory, but we also apply the algorithmic theoretical lens on other disciplines, and so we do have many programs that combine theoretical computer science with physics or math or biology, and even more esoteric things like psychology, AI, linguistics, and so on. So this has been a great venue, and we hope to keep going. And we are funded through 2034, but we hope to, with generous contributions, keep going beyond that point. This is a program, this is part of this workshop on proofs, is part of the program on cryptography 10 years later. So there was a very exciting program in cryptography 10 years ago, and so obviously we wanted to repeat it, but we try not to repeat programs more frequently than about 10 years apart. So this is about the right time to do it. In case you're wondering how programs are chosen at the Simons, the programs are created based on input from the community everywhere around the world. So if you have a great idea for a program that needs to happen here, please do send in a short proposal. We've made it easier for you now. And then we will give you feedback and ask for a longer proposal if we think this has a possibility. Of course, don't do cryptography for another 10 years. And the last thing I want to say is that I want to thank the organizers of this program, of this workshop. I believe Abhishek, Dan, and Yael. And thank you very much. And look forward to having a great workshop. One last housekeeping rule, as you all observed very nicely, no food or drinks in this auditorium. That's been a policy since the beginning. Thank you.
All right, welcome everyone. Very happy to be organizing this program with Dan and Yael. We have an exciting program for you all. So it's pretty amazing how far research in proof systems has come, especially over the last decade, and especially in the practice of this area. But theory is steadily and slowly and steadily catching up. So the program will reflect advances in both of these areas. Today we'll start with a bunch of tutorials, which will cover hopefully some techniques that form the backbone of research in this area. Tomorrow we'll start with more recent advances in practice and then transition to theory. Day 4, we'll come back to practice, focusing on IVC, which is an important area these days in practice. And day 5 we'll try to give you a flavor of some new application domains of proof systems. So let's start with Ale, who will tell us about a general paradigm for proof systems.
Thank you, Abhishek. Can you hear me? Good back there? Okay, fantastic. Okay, so good morning, everyone. It's lovely to be back here. Thank you to the organizers for inviting me. So I have been entrusted with the first talk, an introductory one, and it's always a bit of a difficult balance to have introductory talks because I could just bore the experts or completely miss out on newbies. I think I try to have a little bit of something interesting for both experts and newbies. In particular, over the past, I would say, couple of years, there's been some very nice progress in understanding recipes for succinct arguments, really at the conceptual level. So I'll try to highlight throughout. So we'll start out with a few basic slides to agree on notation, and from there on, I hope I have something new that is both accessible and also interesting for the experts. Okay, so as a plan, I'll primarily focus on commitment-based succinct arguments. Please do stop me along the way if you have questions. All right, fantastic. Let's get started. So today's protagonists are succinct arguments. In short, these are cryptographic proofs that are for computation integrity that are super short and super fast to verify. Cryptographic proofs is just another name for arguments that we use in cryptography. And so these are proof systems for relations. We have instance witness pairs, and we'll also sometimes talk about the corresponding language of the relation. Just briefly to compare the difference between interactive proof and interactive arguments, syntactically they look very similar. Prover and verifier exchanging regular messages. And the completeness property for the proof system also basically the same. The main difference between these two notions is in the security. Okay? So on the one hand, in an interactive proof, you require security against all provers, including all powerful ones. Whereas for an interactive argument, since you're using cryptography, you only require security against computationally efficient adversaries. Okay? It's kind of the difference between the information theoretically secure one-time pad and computationally secure, symmetric key encryption. Okay? Entirely analogous. So we'll focus on interactive arguments today. So more precisely, because you're using cryptography, there might be a few more things you need to keep track of when you discuss an interactive argument rather than an interactive proof. One of them is system setup. You may have some generator that samples public parameters for your proof system. Also, sometimes you're doing idealized analysis and you have some oracles floating around. Okay, whatever. So you have some distribution that samples those oracles for your proof system. So syntactically, it looks maybe a little bit richer than the usual interactive proof, where now the honest prover and honest verifier additionally receive maybe some oracles, maybe some public parameters, maybe both. And of course, you correspondingly adapt completeness and soundness to take that into account. I'll just highlight that in the soundness case, particularly if you care about concrete security, the fact that you have both cryptography and oracles means that you might be keeping track of multiple resources. For example, a number of queries by an adversary to the oracle, as well as the amount of time the adversary is running, so you can keep track of how that affects the security of your proof system, as well as maybe a security parameter that affects how you're sampling things. Okay, so it's just kind of to keep things. This is in slightly more detail what we are going to talk about. A very notable special case are non-interactive arguments. Those are ones where you have a single message from the prover to the verifier. Okay. Of course, there's other settings. I'm just not going to talk about them today. You may have a pre-processing pre-processing phase before proving. This has to do when you deal with ternary relations, so-called indexed relations. I'm not going to talk about it. You may have a reduction rather than an argument, so you're spitting out rather than a decision bit, a new instance, okay, and you're going to continue from there. Again, I'm not going to talk about it. Everything I say today will naturally extend there as well. All right? Good. Any questions so far? Right, good. All right, succinctness. So this is the property that we care about. There is a range of formal definitions. It's kind of a bit annoying to kind of very formally define it, but I will only informally define it. There is succinctness in communication where you say, okay, I want the communication complexity to be much smaller than the witness size. This is about basically compression, right? Or you may want, in addition, also have succinctness in verification where the time of the verifier is much less than the time to decide the relation given a witness. So this is about speed up, okay? So when you hear about succinctness, it could mean either of these or both at the same time, right? And sometimes, even if you have both, you may have a little bit of one and a bit more of the other, or maybe they depend slightly differently on the parameters, so just keep that in mind. The entire reason why we're talking about interactive arguments rather than interactive proofs is that interactive proofs cannot be succinct under standard complexity assumptions. Okay? These are classical results from computational complexity, and that is why we are kind of forced to introduce cryptography to achieve these efficiency notions. Okay? Now, is succinctness the only property we care about? No. There's other things like zero knowledge, knowledge soundness. I'm not going to talk about them, okay? But you can ask me later if you want to. And I'm sure this will be brought up a number of times during today and the rest of the week. All right, so that's what we're interested in, succinct arguments. Okay, that was today's protagonist. So from today, we kind of look back. The way I personally like to view the results landscape is as follows. There are results upon which the entire area is founded. I'll call these fundamental succinctness theorems, also known as hashing suffices. All right? So if you give me a collision-resistant hash function, I can give you a 4-message succinct argument. Alternatively, if you give me something even stronger, an ideal hash function, a random oracle, I can get you a succinct argument even with a single message. Okay? These are results from the 90s. They are, in a sense, what makes everything possible. Okay? And that's where we start from. There is essentially 2 main lines of research in the last 15 years to a first order, okay, that take 2 different optimization functions. One of them is to minimize the assumptions to achieve succinctness. Okay, so that is your goal, and you want to start with as weak cryptographic assumption as possible. So you may ask things such as, let's take the goal of succinct interactive arguments. Can I get by with less than a CRH, maybe a multi-CRH? Okay? Or in the case of non-interactive arguments, can I get by with no random oracles, maybe just a falsifiable assumption? All right? So it's about if-then type of theoretical cryptography implications. Here, one of the main open questions, the holy grail of the area, is achieving succinct non-interactive arguments, also known as SNARGs, from a nice falsifiable assumption like LWE. The other line of work, it takes a slightly different objective function, and that is to minimize costs. Okay? So you want to minimize the asymptotic or also as well the concrete cost of succinct, usually non-interactive arguments. Okay? And here you may allow yourself to use oracles as well as non-falsifiable assumptions. All right? This has led to a large body of work with highly efficient constructions and implementations that aim to achieve the best communication complexity, the best prover-verifier time and space. Okay? These 2 lines of work do have interactions, but to a first order, it's either are you optimizing for assumptions or are you optimizing for efficiency? Okay? Today, I will focus on this second line of work. Okay? There is different principles that hold at high level in the other line of work, and I think that will be touched in other talks this week. Any questions? Good. All right. So that is the results landscape. And so I personally started working in this area around 2008. And at that time, again, to a first order, what we had was the fundamental succinctness theorems. And then subsequently, during a few years, there was a kind of very exciting interaction between efficient constructions, implementations, and applications that led to very exciting growth in kind of techniques, tools, results, that led to rather rich SNARG-scape. And in fact, around 2017, we started planning for a Simons program that took place in the fall of 2019. This was with Eli Ben-Sasson, Yael Kalai, Rafael Paz, and Mike Wolfish. Okay? And a big component of this semester back then was proof systems. Okay? And if I look back, I think there is a lot of beautiful and exciting works that came out of collaborations that were born during that kind of very, I think, exciting semester. But that was 2019. By now, we have a very big ecosystem. And since everything is AI today, I'm going to call this AISC. What does that stand for? That is the academic industrial SNARG complex. Okay? It truly is an impressive, large ecosystem. There's been hundreds of millions of dollars pumped into this ecosystem that has then, I mean, not necessarily in basic research, but certainly some of those ripples have gone back into basic research, helping bring in new talent and new ideas and new challenges as well. So this is the point where in a talk, I think it is customary to bring a few well-known logos of companies. Since it's Monday morning and we all kind of need to wake up, I decided to do something a little bit different. And I dug up some less known companies that have been either contributing to the SNARG kind of ecosystem or trying to benefit from its success. So, for example, there is the consulting mega group, the proofs and profs group. Okay. There is probabilistic airways. They have the largest fleet of reductions that will get you safe and, most importantly, sound from problem A to problem B. Zero capital, of course. What else? There is the very successful apparel company, Just Prove It. The incubator SNARG Tank, among the hosts, there is, you may have heard, Mark Hypercuban. Of course, there is the law firm Merlin Arthur. They've done sort of great work, exposing and bringing strong court cases for abuse by local governments of public coins. SNARG Justice League, okay, like for social justice. Of course, the iconic commercial development, SNARG Tower. And last but not least, the kind of risque and long-running cabaret show, Midnight at the Montgomery Ladder. So you may not have heard of some of these efforts, but all of them are related to this AISC.
So no logos?
No logos. I said I was going to bring up logos. All right, so this, jokes aside, it really is a rich ecosystem and there's a lot going on. So let's come back to science. And so where do succinct arguments come from today, at least efficient ones? There are two complementary tools coming from computational complexity and cryptography. So on the one hand, you have some form of probabilistic proof that is going to be secure against all-powerful adversaries, inefficient ones. And it will, now, by being information-theoretically secure, it cannot be an interactive proof. We already said that. But it will achieve succinctness in some query model. All right? On the other hand, you have a commitment scheme, because by being a kind of a cryptographic notion, it is secure against efficient adversaries. And it's going to provide you with succinct commitment and openings for that query model of the proof system. You combine these two using a rather intuitive transformation. For today, I'll just call it commit then open transformation. There's like a variety of them. And you'll get a succinct argument out of that. The proof system will primarily determine the type of computation that you handle, a machine or a circuit, for example. Whereas the cryptography is going to determine, well, the cryptographic costs, maybe the setup. Do you have like a public or private coin setup? For the most part, it will determine whether your proof system is pre or post-quantum. So each of these tools kind of contribute some aspect to the resulting succinct argument. So what I'm going to go today, so what I'm going to do now is I'm going to focus on first an interactive argument case, and I'm going to go through a sequence of iterative generalizations, starting from something you probably have already seen potentially a number of times. But then you will see that by sort of extending what we know about this basic case, we're going to end up in a fairly general and powerful setting where essentially the same theorems hold. And these provide the theoretical foundations of today's kind of succinct arguments, at least on the kind of efficiency side. Before I do that, are there any questions? I mean, I see that you guys are all kind of, I mean, nobody's asleep yet, but please do ask questions if they come up, okay? All right. All right, let's get started. So we're going to start with one of the fundamental succinctness theorems, that is Kilian's protocol, okay? It is a protocol that, according to the recipe, brings two tools, a probabilistic proof and a commitment scheme. So which ones are they? Well, tool number one, the proof system, is a probabilistically checkable proof. Diagrammatically, it's like this. You have a prover that writes down a long string pi over some alphabet. So you have L symbols over alphabet sigma. And the verifier is going to make queries to this proof string. A query consists of an index, and the answer for that query consists of the symbol at that location. It can make, possibly even adaptively, some number of queries, and at some point it says accept or reject. Okay, that's a PCB. You probably have seen it elsewhere. This is the diagram we use for it today. The other tool from cryptography is a vector commitment scheme. Okay, so you may have some setup, whatever, just it is what it is. And then it gives you an ability to commit to a vector, right? This string of symbols can be viewed as a vector, and you can feed it into the vc.commit procedure of this commitment scheme, and out will come a succinct commitment to that long vector. That's the commit phase. As you know, a commitment scheme has a commit phase and a reveal phase. So in the reveal phase, what will you find is you have a procedure that says, give me an index into the vector, and I'll produce a proof that certifies the value at that location. And how do you check that? There is a checking algorithm that receives the proof, the claimed value at that location, as well as the location itself, the commitment against which you're checking, and it will tell you whether it's happy or not. Okay, so here the intention is to check, is it indeed the case that, for example, at location alpha, the string pi that was committed under CM really has value. I already have some notation and inconsistencies here. That should be Q, not alpha. Let me fix it on the fly. Opa. Despite the number of times I looked at this thing. Opa. Good. All right, so that is to check that if you look at the qth location of the proofs of the committed string, you will get the value A. Now, more generally, you may want to decommit or reveal more than one location, so you have some subset of indices, and your claimed answer is going to be a function from that subset to the alphabet. Okay? So that is what is a vector commitment scheme. A notable example, of course, is the Merkle commitment scheme, where your public parameter is a hash function, collision-resistant one, and you pairwise hash your string in this fashion. And if you want to reveal a certain location, you just give me as a proof the siblings of the nodes on the path from the place I'm revealing to the root. Okay? Anyways, you've all seen Merkle commitments. I'm just pointing out if a vector commitment didn't make too much sense, think about it as an interface around the Merkle tree. Okay? All right, good. So with these two tools, there is a extremely natural, beautiful protocol that achieves the succinct argument. That is Kilian's protocol, where you VC commit to the PCP string, and then you subsequently VC open to the queried locations. So here's how it looks like. You have the argument prover and argument verifier. The argument prover will run the PCP prover to obtain the long vector. It will VC commit to it, send the commitment to the verifier. The verifier will receive randomness, so we'll send randomness to the prover, who can then locally emulate the PCP verifier, inducing some query set. And then the argument prover will kind of determine the corresponding answers at that query set, and then produce a corresponding opening proof to be sent to the argument verifier, who then proceeds to check the answers and the proof, as well as emulating the PCP verifier on the fragment that was received. Of course, if at any point during this emulation the PCP verifier wants to query something that wasn't received, then you reject. Okay, so this is the canonical construction of a succinct argument. This is also where maybe some of the experts might be bored, and I think starting from the next slide, I will start talking about some new things that we know about this protocol. Before I do that, though, are there any questions? Yes. Yeah.
Just to confirm, this framework that you're describing, does it capture things based on linear PCPs?
It will, yes. I will get to talk about a very generic setting where, as a special case, linear queries will be as well.
Yeah, but the non-interactive linear, like things like growth 16.
Oh, no, sorry, I kind of didn't talk about it, but I had it in the bottom left here. I was kind of maybe rushing through this slide. Not in this talk, are linear-only encodings, which is a different. I don't really know how to see these as commitment schemes. They're slightly different. You can also use linear-only encodings and linear-style probabilistic proofs to construct succinct arguments. They're not in this talk. I'm also not going to talk about sum check arguments, bulletproof style things.
Nor about obfuscation-based proofs.
Or obfuscation-based proof, yeah. Yeah, thanks for the question. All right, more questions? Good. All right, so that's a protocol. It makes sense. It's reasonable. Actually, let's just go back here for a moment. Why does it make sense? Because look, you have a PCP. The PCP verifier is succinct, given that it can query into a long string. Querying to this long string is not a thing we can do in the real world. It's like an idealization, right? Like having this oracle. So the vector commitment scheme allows you to implement this query model interactively. Succinctly commit first, and then after receiving the randomness, for emulating the PCP verifier, you can succinctly decommit. All right? It's like very standard kind of commit then reveal type of a template that appears a lot in cryptography. So what do we know? So for Kilian's protocol, we have two incomparable security analyses. There is one that we can think about it as a black box rewinding proof that takes the argument adversary and reduces it either to the security of the PCP underneath or the vector commitment underneath. And one way to express that security is as follows. Okay, so imagine you have some rewinding proof. You have your security reduction is going to be running some number of times the given argument prover, the malicious argument prover. At some point, it's going to have to stop because it runs in polynomial time. So intuitively, you're going to have some trade-off. The longer you make this reduction run, the less you're going to pay for some additive error. So that additive error is this epsilon here. So for any additive error epsilon, you can bound the soundness error of the Kilian's protocol in terms of what? Well, surely you're going to have to pay for the PCP soundness error. That's this thing over here, epsilon PCP. And then you're going to have some error that comes from the vector commitment scheme. So what's the property of a vector commitment scheme? Well, that is going to be something that we call position binding. Okay? That is the natural security property of a vector commitment scheme. What does it mean? It means this. So you have some adversary. It says, I'm going to output a single commitment and then a bunch of different local fragments with corresponding proofs that I claim are like valid openings. As long as all of them are valid openings, I can then ask, OK, is there an explanation for that? And I want there to be an explanation. So an error is like when there isn't. If there isn't a global explanation that explains all these fragments, then I call that the adversary wins. Okay? You may have seen position binding written slightly differently. It's the same thing. I'm just rewriting the predicate this way. Okay? So if there is no explanation, it means like somewhere, somehow, these fragments might overlap and say inconsistent things. That's the only way you wouldn't have a global explanation for these local fragments. That's your error. And of course, this error might depend on the running time of the adversary. So you have this parameter here, right, that the bigger it is, like, the more easier it could be to attack the scheme, right? Yes?
Isn't this usually like negligible and RPCP is like it seems to me like they're different. They're very, like the epsilon and epsilon PCP can be pretty big, you know, even constant, like 0.01, and this epsilon is like the collision. It's like usually negligible.
True. This one is a concrete analysis, so we want to know what it is, right? But of course, asymptotically, we care that if this one is polynomial, then this one is a function that vanishes faster than any inverse polynomial. It's negligible, right? This can be proved, okay? But because we're in the business of efficient kind of succinct arguments, we care about how are we going to set security parameters, or like, do we have a clean enough understanding of the security to the point that we get an expression that makes sense, right? So this is a concrete security analysis type of thing. And so we have a parameter here. And the smaller you want your additive error, the longer you're going to have to pay for the adversary that attacks the VC scheme. Okay? You also have a dependence here on the proof length, because of course, every time you rewind the adversary, you're going to get a little fragment, right? But in general, like the thing you're talking about has length L. Okay? All right, so this is, yes?
So what is the difference between this definition and simply requiring that the adversary can output a single input point location with two different values.
That one can be expressed this way. If you restrict the answers to be single points, saying that there is no explanation simply means that for that single point, you have two different values.
But aren't they equivalent?
The parameters are fixed.
Yeah, you can sort of reduce them to one another with the Merkle tree in particular. They are equivalent. You will have some slightly different parameters here. The natural definition for this reduction is one where you allow your adversary to output more things at once. Otherwise, you would have to have another security reduction to go from here to the more restricted one.
So you're losing the tightness of the reduction if you use the simpler definition?
Like if you have a specific construction of a vector computing scheme, you might as well directly fulfill and prove the property that is most convenient for that reduction. Because there are two reductions, right? There's a reduction from Kilian to PCP and VC, and you have another reduction from VC to whatever underlying complexity assumption you have underneath. Think about it, collision resistance of the CRH, so of the Merkle tree. Sorry, of the CRH underlying the Merkle tree, right? And more generally, like it could be that reducing this to a simpler one and then to the assumption costs you more than just going from here to the assumption. Either way, for the security reduction, that is the most convenient thing you get for the vector computing scheme. There is evidence, strong evidence, that this trade-off is inherent. Okay, this is somewhat related to kind of you can think about it similar to lower bounds on black box simulation of zero knowledge. Anytime you have like a black box winding argument, you have this type of trade-offs. Okay, and this can be made somewhat formal. If you get bothered by that, an alternative around it is you can have an expected time reduction, right? You can let your security reduction run in expected time that is going to lead to an expected time adversary, and you're going to need to assume the underlying VC scheme is secure against expected time adversaries. Yeah.
Well, this definition, can it be seen as like the soundness of a simple sort of argument where you have the witness being the proof string, the statement being like the commitment answers and proofs, and then the relation being that all the VC checks are verified?
I'm not sure, because soundness to me is about one execution, whereas here, in a sense, like you have multiple outputs of the adversary, so it's kind of already, it's more of a.
So it's a multi-instance relation.
I'm not sure how to cleanly see it as soundness. Like I'm personally, from a philosophical standpoint, quite happy thinking about it as a sort of position binding. Yeah, it's kind of because where would these multiple instances come from? Well, eventually they're going to come from rewinding, right? And rewinding, it's already inside the security reduction, right? Whereas soundness is like telling you one execution or a proof system on an instance not in the language, right? So they're like a slightly different. I'm not sure how to do that. Anyhow, so these are like the two main sort of kind of reductions that we know about Kilian. You could also say, all right, actually, I'm not happy with these security parameters. I want more, okay? So you have another option, which is to have straight line extraction in an ideal model. So in this case, what you can do is you can assume the underlying vector commitment scheme is so-called straight line extractable. Okay? This is akin to thinking, for example, of the Merkle tree as being built not from a CRH, but from a random oracle. Okay? And you can have similar, like analogous things for other types of vector commitments. In this case, you're going to get a different bound, this one. And what's the property? Well, this one over here. It basically says you have a commit and reveal phase. During the commit phase, you produce a succinct commitment. The extractor is going to look at the query answer trace up to that point, produce a candidate decommitment, not decommit, the underlying message. And then in the reveal phase, the adversary produces a local fragment with a proof. And then it wins if what the extractor found and what the adversary opened are inconsistent. Okay? So this is not a position binding type of thing. It's much stronger. It's saying it's an extraction type of security property. Anyhow, these two have two different rules. These are to sleep good at night, that nothing catastrophic is going to happen for Kilian. And this is generally for setting parameters. And the gap between them is not enormous, but it is there. If I remember correctly, for example, for the case of Merkle tree, if you use one over the other, you're going to get with security parameters that are about 2.5, 3 times away from each other. So they're not very far apart, but you don't want to do that. Yeah. All right, so that's Kilian, and we take this as a starting point. All right, are there any questions? From here now we want to kind of move on and do something much more general. Yes?
You mentioned the trade-offs. Are there lower bounds? Or?
Yeah, so there are some lower bounds. I can, for example, if you were to completely get rid of this, or rather, you can basically show that Kilian, you can program Kilian so that its soundness error is an upper bound to the soundness error of a Schnorr identification scheme. And so if you can significantly improve this one, then it would improve the state of the art on the Schnorr identification scheme. So that's a type of lower bound, okay? I believe one can prove stronger things, specifically talking about that dependence, but they're not known yet. I think it's a good question. Okay? All right. More questions? All right, cool. So, but that's just so-called point queries. You can think about more generic, more general query models. You can think of a query class Q. A query class Q for proof strings in sigma to the L is just a set of functions that map proof strings to some domain, okay? And with that query class, you can think about Q functional equivalents of PCPs and vector commitment schemes. So for example, a Q functional FPCP would look like this. The queries now, rather than being point queries, they're just something from the query class, and you get back whatever the answer is. Similarly, you can think about a functional commitment scheme for that query class that looks pretty much like before. You have a setup. Now it's FC instead of VC for functional commitment. And you commit to the vector like before, except that later, when you open, you're going to have to pick a query from the query class to be checked later against some answer. And more generally, you're going to have a subset of queries, maybe like 5 queries or 10 queries, and you're going to have a claimed answer function from that query set to the answer. Okay? And the aim here is to check, is it the case that if you evaluate, I'm going to use this notation, set Q of pi equals answer is saying apply each of the queries in the set and see whether you get the answers in the answer function. Okay? So this is like a natural generalization of what we had before. This natural generalization implies a corresponding generalization of Kilian, right? So this commit then open strategy extends to any query class, at least syntactically, okay? Where you run your FPCP rather than PCP, you run the functional commitment scheme, you get back the randomness. The randomness is going to lead to a subset of queries to that PCP string. And then you're going to use the functional commitment scheme to open the same thing, okay? Questions? Like, as far as the intuition is concerned, like there was nothing very specific about the fact we have point queries, right? Now the question is, okay, fine, this makes sense syntactically. Is it secure? Actually, before that, I have some examples of query classes. The ones where you look at single elements of the proof string, these are, we can call them point queries, right? They look like this. But in general, in the literature, people have considered a bunch of different query classes. There are linear queries. You take a linear combination, your desired linear combination of every element in the proof string. You can have so-called univariate polynomial queries. You view the proof string as coefficients of a univariate polynomial, and the query specifies where you're evaluating that polynomial. And you have a few other, including some complicated ones. I'm not going to get into this one, but for example, this structured polynomial queries, they appear natively inside, for example, Plonk. Okay? Whatever. These are just some query classes. The point is that thinking of these query classes, they make this commit then open transformation extremely flexible. All right? Questions?
The last one, what is the query? What is the
So the proof string can be viewed as like some collection of polynomials, univariate ones. Sorry?
FNG is the query.
No, FNGs is the message. The query is these kind of other low polynomials and evaluation point. It's basically saying here's a univariate evaluation point, kind of like this one. And then I'm also going to specify some circuit of how to assemble these polynomials evaluated at alpha. Okay? All right, so yeah.
This might be too detailed, but would you say that all of the higher level queries reduce to point queries eventually, like in the proof of them? One
can reduce FPCPs for many query classes to this one using proximity tests and things like that. But that is if ultimately, anyways, you were going to use a Merkle tree. You don't have to. There are some cryptography that natively works for other query classes. Okay, and then you have like the corresponding trade-offs of whatever it was of the two different tools. Okay, yeah. All right. Good. So, what security can we prove? So, like before, we can have two incomparable security analyses for this functional extension of Kilian protocol. You can have a black box prover rewinding proof, okay, where you have a trade-off. Now, this time, the exact trade-off depends on the query class, okay? So you're going to have some soundness error of the FPCP. You're going to have a error coming from the function commitment scheme. That's something called function binding, okay? It's the same property of before. It's saying the prover gets to output a single commitment, a bunch of fragments, okay? Now, you really shouldn't think about them as fragments anymore because these are just generic queries, so they're not really fragments. These are like answers, right? And it wins if all the outputs are valid and there is no global explanation that explains all of these queries, okay? That's function binding. And then you also have other things to pay attention. I'll give an example. Let's say you're doing univariate polynomial evaluation as a query classes. So each time you see an answer, that's an evaluation of a polynomial. So now you have this evaluation, that evaluation, that evaluation. In the security reduction, you're going to have to run some inverse FFT to recover the original polynomial, right? Now, in general, for a whatever query class, you're going to have a bunch of answers, and you're going to need to pay for the cost to infer what was the message given all of these answers. So it is what it is. We call this a solver, all right? It is a thing that gives you anything that is consistent with those answers, okay? So you pay for that in the security reduction. And then there's something called the tail error, okay? Intuitively, it is basically, in the security reduction, like in the case of Kilian, you run. At some point, you say, well, I'm out of budget, okay? So one of several things happened. Either I have a good PCP, or I violated function binding, or something weird happens where you're not violating function binding, but you have a query to a place that you haven't seen so far, okay? And in the case of point queries, it's kind of very simple. The analysis is just kind of degenerate, what happens. But for a generic query class, you have to write down an experiment that captures that case in the security analysis. And for any particular query class, you have to kind of analyze that thing. Anyhow, for all the query classes I've shown in the prior slide, in the end, it ends up being the same thing. You can set parameters so you have the same 1/epsilon versus epsilon trade-off. You can prove this. But in general, it is something. Okay? Yes?
For the function binding error, like the game that you wrote, so that first we're given public parameters should specify the QI also, right? Like there's a QI.
Yeah. So
the answer and then the proof.
The way you specify this function is, in particular, you provide me with the domain of the function, which is the query set that you claim. Yeah.
So there's also QI,
sorry.
and PI.
I didn't say that QI is deducible from ANS I.
I see. So that it includes.
Sorry about that. Yeah.
Okay.
Since this is all in the information-theoretic domain, can this be somehow reduced to questions in like the complexity-theoretic study of query complexity or communication complexity?
So this one is information-theoretic. This one need not be. In general, it's not because it's.
But in generic models, right? Okay.
In generic models, I think it's a good question. I don't have sort of specific results I can point to that, but yeah. And actually, this relates to the second one, because if you are here without oracles, right, you're doing like standard model cryptography, but you could also consider, analogously to the case of the Merkle tree, some straight-line extraction, okay, where now you have a straight-line extraction error for your function commitment, And the security property that you get is precisely like the natural thing that you would write down having seen the one from Merkle trees. Okay? It says, commit to something, give me a trace. The extractor looks for a candidate kind of message underneath, right? And provided in the reveal phase you give me a good answer, I'm going to call the adversary if it wins if what it provides in the reveal phase is inconsistent with what the extractor found at the end of the commit phase. Okay? And so this way you can take what we learned from Kilian and bring it to this very generic setting of like any query class. Okay? Yeah.
The extraction thing is one instance versus multi-instance for the rewinding. Is that?
In the particular case of Kilian, it's enough to extract once. When you consider kind of other settings, for example, after Fiat-Shamir, you need to extract multiple times. But in this case, this is enough. This is the property you want for Kilian. Yeah. More questions? Good. All right. So, okay, we're doing good on time. Yes. All right. So that was a functional extension of Kilian. But something that has become an important lesson over the last 15 years is that in probabilistic proofs, very often, with more rounds, you get much more efficiency. Now, the number of extra rounds that you need doesn't always have to be a lot more, but generally more than one is something that you want for some reason, almost always. So it is important to understand what happens there, right? And why do you want that? Because, I don't know, maybe you want to run the sum check protocol, maybe you want to do some sort of divide and combine strategy, maybe you're doing out-of-domain sampling, whatever. There's like a bunch of beautiful tools out there that care about interaction. When you realize that, then you see that you no longer fit this PCP or FPCP comfortably, and so now you want to consider a functional analog of an interactive oracle proof. So that would be an interactive protocol where at each round, the prover is going to write down a proof string over some alphabet with some length. The verifier is going to contribute some public coins, and this goes on for some number of rounds k. And at the end of the interaction, there is queries by the verifier, and maybe there's a query class for round 1, a query class for round 2, and so on and so forth, right? There's different query classes per rounds. And now you have some generic kind of functional extension of an IOP. Yeah? Good. And why do we, once again, why do we look at this generalization is because we can fit inside this interface far more efficient protocols than we could from before. Okay? Now, if you do that, this commit then open transformation can be naturally adapted to this multi-round setting. You just do it for each round. Right? So you now have a new interactive argument. And within this interactive argument, which is more interactive than before, you have this FIOP. And you're going to run the prior strategy, where each time you get a proof, you apply the corresponding function commitment scheme for that query class. You get back an answer that lets you deduce the next proof string. And you continue in this fashion until the last round, where you produce the final commitment, you receive the final randomness. Now you can locally emulate the FIOP verifier to deduce all the query sets, okay? And for each of these query sets, you're going to produce some answer and proof to send over, yeah? And at the end, on the argument verifier side, after the interaction, is going to check that all the function commitments are happy, and moreover, that the FIOP, given the answers to the queries, will accept. Okay? Good. So, yeah.
Say a bit more about what do you think of as efficient here? Because I mean, in a lot of models, communication costs much more than anything. So, how, in terms of verifier time.
Yeah. So this relates to the second part of the talk that I will get to very soon. This interactive argument is usually just a stepping stone. Okay? We then remove interaction using something known as a Fiat-Shamir transformation, and then this costly interaction kind of intuitively goes away. All right?
All of this is underneath the Fiat-Shamir?
Yes, yes, right. But of course, interaction might be the most expensive thing anyways, but this makes sense because we know it will go away. Good question. More questions? Yeah.
Or maybe you want to say it's proof size. It becomes like proof size.
Excuse me?
Maybe you want to say it becomes like proof size after you do the Fiat-Shamir.
Yeah, of course, if you have more rounds, more commitments, once you do Fiat-Shamir, all these guys are going to be part of the kind of argument you send non-interactively. So if you have way too many rounds, right, then that is not something you're going to be happy about. Now, fortunately, the things that generally care about interaction a constant number of rounds or maybe logarithmic number of rounds, thereabouts. Rarely we do more than that. But yes, like highly interactive proof systems will be like slightly less argument efficient, communication efficient than less interactive ones, on average. Good. So you can talk about the security of this one, and again, you can talk about two types of security reductions, a rewinding one, right? So that we sleep tight at night and we have a security proof that works without any oracles. And what you're going to get is like some generalization of what I've shown before. You're going to pay for the soundness error of your FIOP, and then you're going to have to pay for the function binding errors across each of the rounds and the tail errors for each of the query sets. Okay? So whatever, like this makes sense. Or you can do a straight line extraction where you say, okay, each of these function commitment schemes at each round are all straight line extractable, and you will get some corresponding analysis like this. Okay, that will give you slightly better parameters. All right. More generally, you don't even need to have k different function commitments. What you really want to have actually is a batch FC. Okay, so one single piece of cryptographic kind of equipment that will handle all query sets, Q1, Q2, up to Qk, because there are some things that people do in practice that are not just run each of the function commitments individually, right? But for example, you might say, hey, I'm opening Oracle 1 and Oracle 2 at the same location. Rather than receiving two opening proofs separately, I will have one more round of interaction and receive one opening proof instead, okay? So the real interface you care about is some sort of batch FC that talks about Q1 up to Qk, all right, all together. And a particular way to achieve that is you have separately FC1 and up to FCK internally, but that's not the only way to do it. That's just the direct way to do it.
Also related to the commitment obstruction, what you really care about is independence between certain things, and commitment is one means of enforcing independence, but you have other means. So to what extent, for instance, the growth 16 question,
yeah,
linear only is a means of achieving independence without a commitment. So
yeah, I mean, I'm focusing just on commitment
but
based.
Is this example an instance where you achieve independence by other means, or it's a instance?
I mean, this is still a commitment, right? So this is you have the commit. You're still running commit individually at each round as you go along, and this is just about the opening later. So it's like, okay, I would view it's squarely underneath the umbrella of commitment-based succinct arguments. It's just the opening phase is now like one monolithic thing that does something potentially more efficient at the end of the protocol.
But I don't understand, if you batch all the commitments, then it's the same as one commitment for different function class.
No, I'm not saying I'm batching in a particular way. I'm saying in general, you're going to have to, okay, you have individually commit for the first round, individually commit for the second round. Okay, now you're done, right?
Yeah.
Before I said.
Now you open them together. The only thing.
Yeah, exactly. It's just the opening, right?
Just
like
opening, okay.
One way to open
Yeah.
is to individually open each one of them, right? But there might be better ways to do it.
You can batch open.
Often there is,
Yeah.
right? And so when you do a security analysis, you want to express that, right? And so you have this interface.
Don't you also need a joint security notion for the functional commitment so that they don't conflict with each other?
You can talk about position binding for this batch FC, okay? And you can talk about straight line extraction for this batch FC. And that's a security notion that will feed into that. Yeah.
So this way the proof is sent at the end, but the answers are sent after every round, and you're postponing the check, only the check of the proof at the very end?
So the commitments come on the fly. Yeah. Then you have to send the answers because we have to fix the theorem we're proving in a sense, right? So you send me the answers, and after the answers...
But without proofs. You send
without proofs, right? We have just some interaction that is like a tantamount to a bunch of proofs. All right, good. So we have, I think, 10 minutes because we started 5 minutes after, right? So Good. So about to kind of shift gears and talk about non-interactive things, just a couple of remarks, I think very interesting ones. So far, I only talked about, that should be public coin. How do you still find, I've seen this line like a million times. Okay, so far we've talked about public coin IOPs. Okay, good. So everything I've said holds for that. Notice that, of course, you can define also as a bigger class private coin IOPs, where you don't require the verifier to send kind of pure randomness in each round. It is clearly insecure to do the commit then reveal for a generic private coin IOP. Why? Because the soundness notion of a private coin IOP doesn't say anything about what happens if the prover learns mid-interaction that you did make that query to that oracle, right? So really, the commit then open strategy can at best make sense for a class that you could consider public query IOPs. So these are private coin IOPs where you additionally say that it's OK for the prover to learn when you make queries where, right? Because then in the compiler, that you're going to have to tell the prover, right? So this is at best. The interesting thing is that the things I talked about today do not extend to all public query IOPs, even though that is the class you would expect to get. What you can prove is you can get all public query IOPs that have an efficient so-called random continuation sampler, okay? And there is a very interesting gap, and it probably cannot be bridged, that if, so there's conjectures right now that say that if you could somehow prove you could have a black box security reduction for all public coin IOPs, then one-way functions do not exist, okay? And this is analogous to other sort of black box lower bound results that happen for proof systems, okay? Where you really care about like a random continuation, okay? Anyways, this is to say that there remain very interesting open questions, even about like very basic protocols, okay? Like even like a 2-round IOP with vector commitment. Yeah.
Sorry, could you say again what the conjecture?
The what, sorry?
The conjecture.
That if you can cover the entire orange area, then one-way functions do not exist. Yes.
Any interesting example of such proof system which is not public coin?
No. So this is primarily like exploring this area. I think is like more of a theoretical cryptographer sort of type of interest. We live in a world where we are particularly lucky that almost everything we care about is just public coin, in particular public query.
Yeah, the almost. Is there anything outside of the almost? I don't know the area. I'm asking you.
No. Like there are semi. Okay, here's an example. Okay, there are some necessity results. This is one example. I give you a generic SNARG in the ROM unconditionally, and you can derive from it an IOP. This essentially tells you that IOPs are necessary for constructing any like SNARGs in the ROM in general. The IOP you construct, okay, is kind of actually that's not a good example. Actually, sorry, I was going to focus on adaptive querying, but it's not. Yeah, I don't really have great examples. I don't have great examples for that. Yeah. The almost is most. I think it's maybe more of like a legal type of protection. Like so almost anything is just so not to make absolute statements.
Graph non-isomorphism proof, isn't it?
Yeah, but that's more of an IP. Like I'm thinking of like IOP, natural IOPs. Yeah. Yeah, so there's a question also tightness or rewinding. I briefly mentioned before. This is kind of the best that we know today. It is, once you work out the parameters, for example, for Merkle trees, it is tantamount to this, okay, once you balance the two sides. And doing much better than that would imply breakthroughs in Schnorr. And this is kind of what I said before, that some trade-off and a specific trade-off might be inherent. You could also talk about post-quantum security. It's complicated. And it's mostly known for now for vector commitments, not function commitments. And you can have, again, two types of security reductions. You can do a black box quantum rewinding, or you can have straight line quantum extraction in some idealized model. Both of them are rather complicated, but with enough sort of effort, they can be done. Okay? Again, also important for future proofing this commitment-based succinct arguments. Okay, so I have 5 minutes left. I need to choose what to do. Yeah, I think the next 3 slides are enough, and that's okay. Any questions before I get there?
breakthrough in Schnorr?
Doing better than square root. So in Schnorr, the way I understand it is you can have either strict time or expected time reductions. The strict time reduction will cost you square root of the discrete log error. Okay, so doing better than discrete log is not known, and improving significantly this one would imply an improvement on that square root bound. Question. All right, so onwards. Okay, so I'll just say a few words about a non-interactive case. This goes back to the question, how is adding interaction more efficient? Interaction is generally additional costs, round trips, and sometimes it just flat out prevents some applications, or for example, just posting a proof on a website, or these days on the blockchain, right? So the point is that so far we've just talked about this commit then open transformation. It gets us only this far. And thereafter, for now, essentially everything we do falls under an umbrella term that refers to multiple techniques, the Fiat-Shamir transformation. And if before we were working at the intersection of computational complexity and cryptography, now working with Fiat-Shamir, we're working at the intersection of crypto and hope. Which is not a great intersection to be at, but that's where we're at.
The entire field of crypto is basically.
That's also true. It's hope turtles all the way down. But there's different units of hope, and fair point. A key realization is that the interaction in our interactive argument arises due to two reasons. Either we are emulating the interactive part of the FIOP, or we are emulating the interactive part of the opening phase of the function commitment. If both of these building blocks are public coin, then the resulting interactive succinct argument is also public coin. It need not have been, right? But this construction is, and that's fantastic, okay? Why is it fantastic? Because, of course, we have the Fiat-Shamir transformation. I'll just mention, I think, this slide or next, and then that's it. That says, for example, let's look at the simplest non-trivial case of a three-message interactive argument where we have the verifier speaks once, this randomness. The idea of the Fiat-Shamir transformation is that you're going to derive the verifier's randomness in the prover's head via a good hash function, sampled according to some ensemble. So it looks like this. The non-interactive argument prover emulates this public coin interaction with the verifier by feeding the first prover message, as well as the instance, into this good hash function to derive some randomness, to produce the next message, which is then packaged with the first one as a non-interactive argument. The verifier rederives the randomness the same way and then runs its kind of a post-interaction predicate. Okay? So this transformation has a multi-round analog, and I just want to end on this slide that summarizes the state of affairs. Now, what we want is a standard model security for good sleep, maybe not with the best parameters, but that just tells us nothing catastrophic is going to happen. And then, analogously to what we were doing in an interactive case, we would want some ideal model security for good parameters. Okay? What we have is not what we want. And research is ongoing to improve this gap or reduce this gap. Roughly speaking, you can understand Fiat-Shamir in the idealized model where you pick the best hash function out there. It's a random oracle. Okay? In this case, what happens to an interactive argument is rather well understood. And I rather optimistically wrote this talk, but this now it's not this talk, but you can ask me later. I'll have the slides, of course, available. In the standard model, you would want H to be good, but efficiently computable, not a random oracle, right? And this is severely complicated by the fact that this cannot, in general, be achieved. There are even three-message interactive arguments where no matter your choice of efficient hash function, when you apply the Fiat-Shamir transformation to that interactive argument, you will not get something that is secure. The takeaway is that security in the standard model of the Fiat-Shamir transformation must rely on special properties of the specific interactive argument that you're Fiat-Shamiring. So visually, what happens is the following. You cannot analyze the entire class of interactive arguments with Fiat-Shamir. You can maybe consider some alternative Fiat-Shamir. There is also research that is ongoing, but whatever, put it aside. What we do know today, and you will hear more in the next talk, is that there is a large class of information-theoretically sound interactive proofs, roughly the ones that are round-around sound, where there are good hash functions that are efficiently computable. But that's no good for us because interactive proofs are not succinct. Okay? Well, if we care about succinct arguments, then we care about different region of this picture. What we care about is this region. Fiat-Shamir applied, for example, to this commit then open transformation. Okay, can we hope to understand that class in full? Well, actually, we have counterexamples even inside this class. Okay? And so the state of the art today is that there is a cautious optimism, at least on my part, that there are natural properties that you can focus on the FIOP and FC that would restrict you further and keep inside of it interesting constructions while also give you standard model instantiations of Fiat-Shamir. Anyways, so I think this is a place where I want to conclude. I'll just jump to the end here and say that we talked about how FIOPs and function commitment schemes come together to obtain succinct interactive arguments. In a final step, you apply the Fiat-Shamir transformation. If you care about something far more detailed than this talk, last year, Elon and I completed a multi-year project of writing a book about these things where we have a comprehensive and rigorous treatment of succinct interactive arguments in the random oracle model. This is the QR code. You can go to snargsbook.org. And I think it's time for me to end here. Thank you. More questions? Yes, Ron.
Maybe just as a comment in the last slide or one before that, that I think that the results that we have for SNARGs for P do fall in the regime of giving you succinctness and doing Fiat-Shamir beyond interactive proofs.
Yes.
It's kind of like in the in-between zone.
Yeah, let me maybe bring up that one. Where did it go? Ah, here. Yes, I didn't want to suggest this is the only area. There are other kind of segments, possibly overlapping, of succinct things that are necessarily cannot be interactive proofs, but they're somewhere here.
You have positive results, right?
Yes, for positive results. Yeah. We're not out there looking for negative results, right? Like we get them as a directions, right? Like, yes.
QR code?
Excuse me?
The QR code?
The QR code. More questions? Yes.
Just a historical question. So I think Kilian was 94 or something.
Excuse me?
Just a historical question for you. So Kilian was 94, and you said you picked this up in 2008, and since then there's been this explosion of work. I'm curious, what caused you to pick this up in 2008 after this long?
Me personally, I got back surgery, and I went from spending 20 hours a week rowing to having to do something with that time, and it was research. And the one topic that I picked up at the time was I started working with Eran Tromer, and we started working on proof-hearing data at the time. It was like my first research effort a long time ago. And of course, it was a very compelling type of tool, even more so than a SNARG. And we started thinking with Eli about kind of efficiency. But it was, for me personally, it was an accident that I started doing research. And why proof systems? Yeah, accident specifically. I surely cannot claim to have had a good understanding of a bigger landscape then. I was still like a very junior researcher. Yes?
Random oracle model from Fiat-Shamir is well suited already for those interactive oracle that has super logarithms.
Yeah, Fiat-Shamir is, I would say, extremely well understood in an ideal model. In particular, it is not the case that every interactive argument is secure after you apply Fiat-Shamir. You need to assume more, something called status duration security, which is implied by other notions like round-around soundness and special soundness, for example.
Suppose you have this property, but it's super logarithm runs.
Sorry?
I mean, suppose you have this property for IOP, it's a state restoration function.
Yeah.
Like logarithm runs.
That's fine. That's okay.
That's fine. Oh.
That's okay. Yeah.
So spend a lot of time dealing with exact security, even though you could have said, okay, is a TLDR or a talk which will reap the benefits of you spending time on this precise definitions and epsilon delta, or is just you wanted to give people, what's the best of them?
So, good question. So you could ask, what are the benefits of caring about concrete security, right? So one benefit is, concrete efficiency. I personally, when I do research, I enjoy concrete security from a different angle as well. And maybe that's the one that drives me more. And that is, it helps me clarify, do I have a natural security reduction? Do I have the right assumption underneath that makes most sense for the protocol? So for example, function binding, in hindsight, it of course has the property you want for the underlying function commitment scheme, but I don't think it was clear until extremely recently that that was the property that you want in general beyond vector commitments. And at least anecdotally, this came up in looking at, okay, what does a security reduction look like? Do we have an expression, a concrete security expression that makes sense? And by kind of working on this concrete security expression to make it as beautiful, as natural as possible, that has the side effect of making you really zoom in on the right property for the underlying crypto. So to me, that is the other takeaway. There is not just concrete efficiency. The fact that these guys are negligibly sound in asymptotically, I guess in the end, we knew it, but you can still ask, you can still say, well, what assumption you start from, right? For Kilian, it was clear. For other query classes, maybe less so.
Okay, let's do more questions after
Yes, okay, thank you.